Hey, welcome back to my first day of bringing up this new board. And because of the complexity, I plan to do it in stages. I'll make one section work and the next section, the next section. Please feed the YouTube algorithm by giving the video a like. If you want to see more like this, click subscribe and ring the bell to be notified of new videos. If you want to chip in on my expenses, I now have Patreon and YouTube memberships. But the first thing I need to do is make sure that I haven't accidentally crossed over from a power to a ground, and I'll check a few of those types of things out before I start attacking the board. Okay, looks like that checks out. So my next step is actually use the stencil and apply the solder paste. But you can't apply the solder paste to just a section of the board. So I'm going to have to do the whole board and then bake it with either the hot air gun or my cute little hot plate thing. And that way all of the pads will basically solidify with their amount of solder on them. That's not the best way to put the secondary and tertiary components on later, but it's the only way this is going to work with me doing the board one logical section at a time. So that'll be fun. Okay, I built my circuit board holder where this thing gets held in place. I've taped over the stencil and I've made sure to align the most critical part, which is the USB-C, and it's unbelievably tiny. I had previously bought a new little tube of solder paste. Yeah, that's what it's called. Now it's been in the fridge because that's the way you're supposed to store it, but now I need to let it warm up to room temperature before it will spread nicely on the pads. Well, that came out a bit of a smeary mess, so I'm going to scrape it all off and try again. And that is the ticket right there. If you've ever watched This Old House and you've watched Tommy put bathroom caulking in a bathroom around the tub, he says you spread it on once and you walk away. You don't fiddle with it. And so that's what I did the second time, and it turned out perfectly. So let's go ahead and pick some of the parts that will go down in this area. Did I hit my finger? No. This is really goopy. Don't stick your finger in it. Now, of course, the first two parts I'm going to put down are these two diodes. And diodes have a polarity, so you have to make sure you put them on the right pad and not backwards. So what I have to do is check my parts list to make sure I'm pulling the right part out of the right bag of all the parts right there. And then I also check the board reference, and I can see the diodes both have their band pointing down, and I can also look at the circuit board, and the schematic, and the band is pointing away from the input jumper. So that gives me all the clues I need to make sure I get these puppies soldered in right, because I would suck to do the very first ones wrong. Well, I barely have any parts done, and I already have my first glitch. The part I ordered for my LEDs, they're not LEDs at all. They're straight diodes that have no emitting light from them. So luckily, I think I have some green LEDs on my shelf, and I will try and substitute something that actually does the job. Okay, I found some red ones and some blue ones, so I gotta keep searching. Did you know that blue LEDs were incredibly difficult to actually discover and manufacture in quantity? Go ahead and look that up. It's an interesting story. Well, I did have some green LEDs, but they're definitely the wrong package size. I think they're one step up from what I was expecting, although the pins on the package, they wrap around on the bottom like that, so maybe they'll work. We'll give it a shot. Okay, I've got the first batch in that corner laid down. I'm going to hit it very gently with the hot air gun. Okay, I've got this power supply area all soldered up. I found some smaller blue LEDs, and I think they're even one step too big. And they're so light, even on the lowest blow setting on the hot air gun, they just blow off the board. So I had to solder them by hand. Now, let's see also what I did. Up in this corner, I smeared all the pads on the wires that I was using to test. So I've got to be really careful. If I smear the ESP32 or the USB-C pads, I'm totally screwed. So let's just go very carefully now. Okay, power supply hooked up, meter hooked up to 12 volts. We're going to turn on our 12 volt supply. And we've got 12 volts on our 12 volts, and our 12 volt indicator is lit up blue. Isn't that awesome? Now, the next thing to try is to jumper the 12 volts, and we should get 3.3 volts lit up. Now, let me grab the little jumper thing. Okay, I switched my probe over to the 3.3 volts. I selected 12 volts with the jumper. Now we'll turn on the power, and we've got 3.3 volts. Oh, it worked! And the 3.3 volt LED is lit up, although at a significantly lower brightness level. But that's a problem for another day. What I'm going to do now is try and solder on the ESP32, and I'm going to use my little hot plate instead of the air blower. We'll give that a try. Okay, I plugged the little heating plate into my USB-C PD adapter. I set it to 138, which is maintaining within 1 or 2, so I'll give it a little nudge. And I've placed the ESP32 as carefully as I can on its pads, side to side and aligned. So the next thing is just to put it on here and wait for the solder to melt. I can't do that with 2 hands. Hold on. Well, that was a bit of a disaster. It was melting all the solder on all the other pads except the ESP32. I think because it's such a heat sink that it would take so much heat in order to heat up the entire unit and then start melting the pads, that I was melting every other pad in the vicinity, which is going to cause me some problems. So I'm going to tack a couple of corners with my soldering pencil and then go around and solder each one individually. Okay, the ESP32 is now soldered down. It's marginally out of alignment because, of course, everything slips. Now I'm going to put these components in for Blinky and for the flash and the boot buttons. Okay, I've got this whole ESP32 section soldered in and the JTAG debug header. Technically, I could power it up, plug my laptop in here with the ESP-PROG board, download software into this, and blink the LED at this point. But I haven't smeared any more of the solder paste, but I'm really worried about the USB connector and the UART chip. So I think I'm going to try and solder these into place. Man, cross your fingers. Well, I forgot that each type of solder paste has a specific heating profile that they want you to do. And I found the one that matches the content of tin and bismuth in the solder paste I have, and it's this curve. So for about, say, 75 seconds or 80 seconds, they want you to go from room temperature to 105, then very slowly to 140 at 3 minutes, have a peak up to 160, 30 seconds later, and then drop down. Now that's going to be super hard for me to push the buttons on the back of this little hot plate. So if I go ahead and decide to do this, I'm going to have to invest in one of those reflow ovens with the programmable heat program which would take care of this automatically for me. But we're going to do it by hand and see how it works. Well, it didn't go horrible. I mean, the problem with this little plate is I was pushing the button on the time, but it wasn't able to keep up. So I ended up way behind the curve, yada, yada, yada. But I held it at the peak for the amount of time it asked for and then dropped it down slowly. The UART chip actually looks good on 3 sides, but this side has a couple of solder bridges that I can hopefully fix by hand. The USB-C connector is a big question mark because the pins, I can't physically see the pins. So the only way I'm going to know if this works is to stick in a cable and maybe get a USB-C cable and cut it, strip down the wires, and try and buzz each pin just to make sure I'm getting what I need. Luckily, I only need power and ground and D plus and D minus. So I only really have to buzz out those pins. But it's getting late and I'm going to leave that for tonight. That is just about enough excitement for one day. Did you know that not all USB-C cables are alike? No, they are not. There's about 5 different versions of how this thing can be wired internally, depending on how many wires are in here and how much the manufacturer wants to spend to actually hooking up all 20 pins. I got this really cool board from a guy in Switzerland. If you can see, it's called Caber QU, and all it does is you plug one end of the cable in and then the other end in here. It's a loop back. You don't plug it into a computer, you don't do anything. One end here, one end here. With this little battery, it tests every potential wire in the cable, and ones that light up are the ones that are active. And this is a cheap cable because we know it's connecting ground, V-bus, which is power, 5 volts, D minus, D plus, and CC1, which is the determines by pulling down with a resistor. It tells the power source what voltage to put onto the V-bus pin. So with that in place, I should be getting requesting 5 volts. And then we have another V-bus and another ground. So this is basically the minimum possible cable that will actually be functional for USB-C. You can see there's TX1 and RX1 and 2. Those are extra data channels for the extremely high speed that USB-C is capable of. You can run like full 4K high definition TV over this cable or transfer files at something like 480 megabits per second. It's just crazy, but you got to pay to get the extra wires. Now, this cable can do what I need for that board. All I need is power and ground, D plus and D minus. But I don't really want to sacrifice this cable. What I found was on my shelf was this one. It's USB-C in one end and regular old USB-A in the other end. And this clearly is a 4-wire cable. So what this helps me do is I can test. If I cut this off, strip the wires, I have only 4 wires in here that I can use to test when I plug this into the board. I can test continuity from the end of this wire to somewhere on the board that the pin comes from. So that's what I'm going to do. I'm going to save this cable because, well, joke's on me, because that cable is even worse than I thought. All it had was power and ground. You couldn't even put data through this cable if you wanted to. So it looks like I get to sacrifice that nice little cable over there. All right, I sacrificed the cable. I put the cable in the vise and I put one of my beautiful little surface mount connectors on with the microscopic pins and buzzed it with my ohm meter. And this is what I found. There's actually 3 silver wires, and they are all common ground. The red wire is plus 12. The green wire is D minus. The white wire is D plus, and the blue wire is S bus 1, which is, it's used either as a signal for another low speed data transfer or a microphone wire. So I'm going to safely ignore the blue wire, and then the other ones are everything that I need. Well, kiddos, you're not going to believe this. It works. The silvers go to ground, which is good. The red, I thought it didn't work, but then I checked the schematic. When I touch on the 12 volt or the 5 volt USB test point, it actually goes through a resistor before it goes here. So I checked on the far side of the resistor and it works. The data pins work, except I've apparently swapped D plus to D minus and D minus to D plus. That's happened before. I'm well known for taking the thing in exactly the wrong way, but I can maybe hack that up. Maybe there's something I can do in software, but I cannot believe that this USB-C connector actually soldered enough that I can use it and move forward. So that is super cool. All right, I just plugged my ESP-PROG board into my board, used a micro USB over to my developer workstation, and we are getting the 3.3 volt lights are lighting up. Oh, and the 12 volt light. Yeah, it's probably backfeeding power somehow, but it appears that we are ready to push code into the ESP32. So let's get that set up. Okay, it took me a while to set up my Visual Studio / Platform IO system. I pulled in a Blinky sample. I set up the criteria my platform.ini, and I had to go back to my own video and remind myself of the settings in order to use the ESP-PROG board. And then I tried to upload the code and it just kept saying it failed and nothing would work. And I was going to try to start debugging the board and checking the pins. Then I said, well, why don't I try swapping the cable? I put a new cable in and it worked. The ESP is now running a Blinky 500 millisecond blink on and off rate. That means the ESP32 works. The debugging chain works through this board back to my PC into the software tool and out to at least one pin that is properly blinking the LED. And that is fantastic progress. Good morning. I started up right where I left, but I was getting all kinds of debugging and upload errors, and everything was just really grumpy this morning until it warmed up, and then I added the code to loop the PWM on this pin, which should change the dial, and we are now going up and down through the voltages, and I'm happy with that. So that functionality works. So let's go ahead. I'm going to solder in the CAN bus, even though I have nothing to test it with. It's a very straightforward section, and I can maybe try and test that when I get to EVTV. And then we will start playing with the high voltage section. And the board assembly is complete. You'll see I finished up the CAN bus section here, and I did the pack DC voltage isolation and scaling all through this part. And you'll see some old school 1/4 watt wire wound resistors. Now those are part of the scaling process. You have to calculate your incoming voltage, scale it down with these, and then as it comes through here, there's another divide by 2 scaler in here. And the point of all of that is to get the voltage from your pack divided by this and then divided by 2 again to safely meet the voltage on the pin input of your device. For me, that's 3.3 volts. So you can either work it forwards or work it backwards. And I will, next revision of the board, I'll put some information here about how to do that calculation. And as specified by the really smart person who designed this circuit, these are 1/4 watt wire wound 0.1% resistors. And I had to go to Mauser in America to buy them. But it all looks good. This is the isolated power supply. It takes my 3.3 volts from this side and provides an isolated 3.3 volts here. As the voltage comes through, this is an opto-isolator that isolates the high voltage DC and turns it back into low voltage DC over here. So at this point, these are safe voltages. And then we do another divide by 2 and come in here. So that was a long day of soldering with my magnifying headset. So I will take a little break and then I will test this. And I don't have access to 150 volts DC, but I do have 30 volts. So I will make sure that the scaling comes through to a certain point, and 150 to 30 is 5. So the voltage here is going to be 5 times less than what I would expect from the pack, and that's okay. Okay, it's a new shiny day, and I'm going to start playing with the input voltage measurement side of things. And I realized in order to put the maximum of 30 volts in here with my bench power supply, I'm losing its ability to put 12 volts in here. So I'm going to power the board with the ESP-PROG debugger, which will put 3.3 volts in here, which will flood the board with 3.3 volts, powering the chips that need to run that side. So let's hope this works. Okay, that's interesting. 3.28 volts coming out of the debug board, powering this side. But when I send it over here and through the isolated 3.3 volt DC supply there, the isolated DC to DC converter is putting out 3.643, which is about 10% hotter. There's no actual circuitry that sets the voltage on that thing with any kind of adjustment factor. That's just what it's putting out. And I hope that doesn't affect the scaling, or I kind of have to take that into account in the software somehow. So let's keep checking up the way for the other parts. And according to this very handy voltage divider calculator, the output of R26, we should be seeing 1.247 volts. So, okay, I've got 30 volts running into the pack input terminals. Let me move the meter over and see what we get on the other side of the resistor divider. And now, reading 2.278, which it ain't 1.274. So I either did something wrong in the calculations, I put the resistors in wrong, or I laid out the circuit wrong. So let me go double check everything. Well, yep, I did it. I screwed up 3 resistors. So in theory, R25 and R26 are one resistor. There's 2 of them in series because it might be hard to get a single 1.5 meg ohm resistor at 0.1% tolerance. And what I did is this R27 is not supposed to tap off in the middle of them. It's supposed to tap off at the end. So it should have gone through here to the pin on the chip, and then R27 is the divider right at that point. So let me hack this up and we'll try it again. And there's the bodge wire. I think in any project, if you don't have one, you're not trying hard enough. So I get my 1. And our output is 1.265, and we were looking for 1.274, and I'm happy with the 1/100th of a volt difference. So let's be happy with that and move on to the next part of the circuit. Okay, I'm not going to pretend I understand the intricate details of the transistor driving the optocoupler, and what I'm reading on my voltmeter makes no sense. I get 0 volts on some of them, but the output on the happy low voltage side, which is pin 1, is right there, and we're getting 1.239 volts. That compares with 1.264 we got on the input of this double step in the op amp through the opto isolator to here. We lost 2.5 hundredths of a volt. Does that sound right to you? Yeah. And then after the first stage of the op amp, there's a divide by 2 here, a resistor divider, which should give us 0.619 on output pin 7 of the op amp, which is right here, and we're getting 0.619. Can you believe that? Now all I have to do is make sure it gets all the way over to the pin on the ESP32. So let me check that. So I'm on pin 8 of the ESP32, and it's reading 0.619 volts. So we have 30 volts DC input, goes through all the isolation steps, through a resistor divider, through another divide by 2 divider, and we have a safe voltage on the input pin here. So that's pretty cool. And 6 times 5 is 30. So we should be a little bit safely under the 3.3 limit, which is actually something a little higher than 3.3. So the ESP32 will be very happy with the 150 volt maximum that I could possibly drive this with. For other users of the board, you will have to calculate and get resistors for a proper voltage divider that meets the needs of the maximum pack voltage in your vehicle. Now, let's write some software, see if we can read that in. All right, let's jump over into the software. The ESP32 Arduino library actually allows you to do all of your voltage readings with one simple API called analog read right here. You just tell it which GPIO pin you want. You get back a value from the analog to digital converter that goes between 0 and 4095, which is 12 bits wide. Now, the downside of this, it's easy in software, but the hardware sucks. This is the one huge downfall of the ESP32, is the analog to digital converter is really bad. It's bad in 2 ways. It is what we call nonlinear. So if you would expect 0 to 3.3 volts to go from 0 to 4095 in the return value, you'd be sadly mistaken. As you can see from this graph, it has a big slump in the middle of it, and it's distorted at the bottom and the top. So that's one part. The second part is the 4095 top value isn't even exactly what you should expect when you have 3.3 volts on your input pin. It could be internally scaling it to 3.3 volts, or I've read in other places 3.6 volts, 3.9 volts, whatever the 3.3 volt power supply on your circuit board happens to be, which could be, who knows, 3.4, 3.35. It could drift with time, meaning you can't actually calibrate at once. Or it could be a magic 1.1 volts, and it is just beyond belief that this is so bad. But luckily, the software people at Espressif who make this chip realized that it's bad. So they actually came out with a way that will help us avoid some of these problems. But before we jump to that, I want to show you how bad it is. So what I'm going to do is we're going to use the hardware debugging, which is working beautifully for me. We're going to actually read the value in on this analog pin, and we'll see what the hardware actually gives us. Now I've set the power supply to 30.0 volts. When it goes through the voltage dividers, we get 0.619 volts out, as we saw. This should give us a reading of 767 with a perfect 3.3 volt reference voltage at the top of the scale. Now, let's see what happens. And I'm going to chop out the initialization of this until we hit the breakpoint. Okay, we are now stopped in the debugger. We are waiting to read the ADC, analog to digital converter reading. The number we're going to get back is from 0 to 4095, scaled across the low to high value. We're looking at 767 in a perfect world. So let me jump over one value, one line. Okay, we are now sitting at the next line of code. If I hover over this variable, it will give us the value. It's 579, and this is repeatable. We're getting 579 from the hardware, where we should be getting 767, and this is ridiculously out of scale. It's like 20% off. And can you imagine trying to do this on your own, to apply all kinds of correction factors and building calibration tables just so you can get the thing to do what it's supposed to do from the start? One thing I thought about doing was actually putting one of the cute, tiny little ADS1115 analog to digital converter chips on the board. The thing's the size of a couple of grains of rice, but it's got 4 channels of insanely highly accurate analog to digital capabilities. But I forgot to do it as part of this design. I forgot, and I put my trust in the ESP32 chip, but this is clearly not working for us. So I'm going to stop this, and I'm going to go ahead and set up the software in the alternate way that Espressif gives developers to actually try to read a fairly robust voltage. So I'm going to stop this, and I'll come back to you in a second. Okay, now in order for the Espressif low-level code to help you apply the calibration, you have to call 2 lines of code in your setup. This first one, to calloc, creates space in memory to hold a structure of calibration factors. The second line is a call that actually builds the calibration factors based on you selecting which ADC you want, either number 1 or number 2. The attenuation factor you want, you can go from no attenuation up to 11 dBs. There's a few things. We want 11 dB because this one gives us the full range of voltage input from 0 to 3.3. We want 12 bits to take us to 4096, and we want to try to use the default voltage reference built into the chip, which is apparently at the factory. Every chip goes through a calibration, and this value is burned into the silicon on the chip to tell it, okay, this is the exact voltage that you should use in your calculations for your defaults. Okay, it sticks all that into this chunk of memory called ADC calibration factors. So let's go ahead and step through that. Okay, we just allocated the memory. Now the Espressif code here, this API, these are all the low-level hardware-specific ESP32 calls. I'll start with ESP, ADC, cal characteristics. So we go here and we look in our global variables, and we have to hunt to try and find it right here. So it knows it's unit 1, dB11, 12 bits. It's got some coefficients that it uses for its calibration. The voltage reference was read at 1.114 volts, and it builds some values here that describe the curve of the calibration. And instead of being a linear straight line, it knows there's a curve. So the ESP library did its job. So now I'm going to go down to where we're going to take our first reading. Okay, we are now at the point where we're going to read the raw ADC value from the hardware, so we'll go ahead and do that. Remember, we're looking for 767, but the normal API was giving us back 580. So we're done there, and we're going to hover, and we're getting 582. So we are literally getting the same raw value back from the hardware. But now we're going to ask the ESP library to apply those calibration factors to hopefully give us a proper value. So let's apply this cal raw to voltage. When it comes back, it not only applies the calibration factors, but it gives us back a voltage times 1,000 because it wants to give us back a floating point value. So what it does is it moves the decimal place over 3 places. Now remember, we're looking for 0.619 volts because that's what is actually hitting the pin of the chip. So if I go here and I hover, 617, boom. Sorry, that's about as close to 619 as we could possibly hope for. We are 2 1,000ths of a volt off. And then I apply down here our scaling factors of the big voltage divider, the divide by 2 voltage divider, and then I divide by 1,000 to give us our true pack voltage, which should be hopefully 30.0. Let's go ahead and read it, and it is 29.058. So we are almost a full volt off, 95 100ths of a volt off. Now that's going to have to do with this factor and this factor. So what I will do in the software, because every board is going to have a slightly different, I mean, this is the perfect world of the resistor values, but that's never going to happen. So in the software, I will have a calibration step, which will take this raw, hopefully true pack voltage to the true pack voltage. And then in software, I will apply yet another calibration factor to get the system to think this is exactly 30.000 volts. So we have successfully fought this problem, and we're reading a good voltage into the chip. Now, I remembered this afternoon that I also read in the car's 12-volt bus into another pin. I will perform exactly the same factors to that pin, and if the battery, the 12-volt bus, is running at 13.3 or 13 or 12.9, I will also take that into account in the calibration factors of how I scale the needle gauge of the fuel gauge. So this is very, very, very good and happy. And just before we wrap up, I thought I'd give it a shot and try the USB-C connector. So I plugged in a cable, and I only have a short cable to go to my workstation, so I had to stretch the wires. Tomorrow I'll get a longer cable. And then I set up the parameters in the INI file for reading on COM5 at 115.2. I updated the speed in the init right here to 115.2. And then what happened? Look, I'm getting my serial output is coming through that cable. So it turns out when I was testing the board, I didn't reverse the D plus and the D minus from the connector to the UART chip. It was correct. And I can't believe that my serial port debug statements are now coming out. That's pretty cool. Now, what I did notice is it looks like I'm getting the maximum value on the input pin even though the power supply is off. So maybe I jiggled a wire and I'm now getting a full 3.3 volts on that pin. But that's one more good thing. And as far as I know, I only had one bad wire on the whole board. And that never happens. Never, ever, ever. So I'll wrap up the video and enjoy the rest of your day. Before we wrap up, I'd like to thank my Patreons and YouTube members, Peter Bouvier, Puppy, and Craig, for their ongoing support. I see that a whopping 96% of my viewers are not subscribers, so please go ahead and click that subscribe button because it really helps out the YouTube algorithm. Thanks and take care, and I'll see you in the next video.